Hello, welcome back. Okay, our next example, right, has this setup. Is your index finger longer than your ring finger, right? So index finger, this one right here, ring finger, that one right over there, right? Look at these ugly little hands, right? But you have your index, right, and your ring, index, ring. Okay. Um, so, is the relative finger length associated with gender? Random sample of 460 students in the U.S., high school students, were selected and asked to record if their pointer finger, right, if the pointer finger was shorter or longer than the ring finger. Okay, on their left hand, right? So let's look to the left hand, right? So which of these two fingers is longer? This one is this one. Just go through and record. Okay. Do the data provide convincing evidence at this significance level of an association? Alright, well, what are we going to do? Just as always, we're going to run through a state, plan, do, conclude. Right? But notice this asks about an association, and when we're asked about an association, that's going to be chi-square test for independence. Right? Is one related to the other? Okay, so what's going to be that process? Okay. Well, our state step, right? We want to test the hypotheses, right? Plural of hypothesis is hypotheses. Alpha is 0.05. Our hypothesis is null. There is no association between gender and digit length or finger length, right? And the alternative, there is an association between gender and finger length. What's the evidence that we have? Well, the observed counts seem to show females have longer index fingers, right? Index finger longer, females more than males. Ring finger longer, females less than males. Okay. What's going to be our plan? Well, our plan is going to be to do this chi-squared test for independence if our conditions met. Once again, why chi-squared for independence? Because we're talking about an association. Okay. What is the plan step? The exact same as it was for homogeneity. So go ahead and try that out. Pause the video, come back, check your answer. Pause the video, come back, check your answer. Well, what's our plan? We've got to make sure the random condition is met. It is stated, right? It says that a random sample of 460 students. The 10% condition must be met. It is reasonable that there are more than 4,600 total high school students, right? Why 4,600? Well, that's 460 times 10. Okay. Expected counts. Well, all our expected counts must be greater than 5. We need to find this matrix. We're going to let our calculator do that. Okay. So we're going to go through and do all of our work and then come back and say, hey, look, if it's not met, we can't necessarily trust our information, and if it is met, then we'll have everything done. So we'll leave this blank for now. We're going to let technology do that work for us. So the next step is the do step. Okay. And the do step is very much the same as what we've seen before. So go ahead, pause the video, do the same type of do step as you did for homogeneity, come back and check your work. Have you done this work yet? Right, the chi-squared is going to be the sum of the difference of observed and expected squared all over the expected. Right, we want to make sure that we show at least a couple of our terms. So observed 85 minus whatever is expected all over expected. Right, and observed 116 minus expected, square that, right, all over expected. And we're still going to need to figure out what those values are. Of course, we're going to use our calculator. Look on page 706 of the TPS 5e textbook. If you need help, check your other work, all right, and make sure that you come back and check your answer. All right, are you putting the information in the matrix? We have 85, 73, 42, 44, 100, 116. All right. Go to matrix B, make sure that we edit matrix B to be the same size. That is a 3 by 2 matrix, 3 rows, 2 columns. Then we're going to come over here, right, and do our chi-squared test. Okay, same thing as homogeneity. Right, run through the chi-square test, observed, expected, A and B, right? And there we have our chi-squared, right? So we can write that information down, right? That we see our chi-squared is equal to 2.065. Our p-value, make sure you write it as p-value, is 0.3561, and our degrees of freedom is equal to 2. Make sure we write that down. But still, we have to come over here and fill out our table, right? And please, make sure that you do the expected counts tables for all the problems. Unless it's a really huge expected counts table, right? Write it out for all the problems, including the observed pieces. So, second matrix, let's look at what that table is. If we want to see if we can get it as a fraction, we can do that. And so you can either list the numbers as decimals or as fractions. I'm just going to go decimals with 2 decimal places. So that's 77.97, 42.44, 106.59, 80.03, 43.56, 109.41. Alright, so just go ahead and fill out the table each time. Okay, so we've got that down, and now we can say, hey, 85 minus 77.97 squared all over 77.97, 116 minus 109.41 all over 109.41. Right, so we can make sure that we're putting all the things in the right place, right? So this minus this, that minus that, just keeping things in order. So there we have it. Okay, so all we're left to do is to conclude. Write yours down, pause the video, come back and check. Preferably pause the video, then write yours down, then come back and check. Okay, so our conclusion, same as we've always done. Because our p-value 0.3561 is greater than our significance level 0.05, we fail to reject the null hypothesis. Right? There is not convincing evidence that there is an association between gender and relative finger length for U.S. high school students. Be careful with how you're writing this, right? That we do not have convincing evidence of an association, right? And what's the association between gender and relative finger length? What's the population of interest? U.S. high school students. Make sure you include all of the context. Okay. Of course, we could come in here and we could always discuss information regarding the type of error that you would have, how we could increase power or how we could decrease power, all those types of things. But hopefully you see the process for working through this chi-square for independence. And on the independence, right, we're going to have the work from a random sample, right, which is just looking at our particular variables. All right.